In our previous discussion, we discussed the IV characteristics of a MOSFET. Today we will derive the equation for this IV characteristics curve by increasing the value of VDS and analyzing the tapered shade of the depletion region. Firstly, we will assume that this is the X direction, this is the Y direction. We will assume that the electric field only work on this Y direction. Okay, and the secondly, channel thickness is gradually increases. The channel thickness is gradually increases from drain to source, or in another word, the depletion region is gradually increases from source side to the drain side. Okay, so let's connect the voltage source VDS and VGS. Okay, so from Poisson's equation, we know del square V is equal to minus rho C divided by epsilon, where rho is the volume charge density. So d2V by dy square is equal to minus q into nd divided by epsilon. So if we do the integration, then we will get dv by dy is equal to q into nd by epsilon is equal to y. V is equal to minus q into nd by 2 epsilon into y square. Okay, where this is the voltage across depletion region. Okay, and y is the depletion region width. In my last video, I told you VVI minus VGS is equal to Q into ND H square by 2 epsilon. How we get this equation? When we apply the voltage VGS, the actual voltages will be VGS minus of VBI. Okay, and here we have one minus, so it will be minus Q ND into H square by 2 into epsilon. So this minus will cancel here, then it will be VBI minus VGS equal to QND H square by 2 into epsilon. This is the voltage equation across the depletion region in the linear region. But here we are calculating in the saturation region. So that means the voltage we already know the voltage in this point is how much is the VBI minus VGS plus VDS, and in this point VBI minus of VGS, at here the VDS is equal to 0. Okay, so we can write down the general equation. We can write down the voltage across the depletion region will be VBI minus of VGS plus of Vx. Okay, in this point Vx is equal to 0, and in this point Vx is equal to VDS. Okay, so we can write down this one is equal to Q into Nd divided by 2 epsilon into Hx whole square. Why? As Hx is the depletion region height. Okay, so from here we can write down Hx is equal to 2 epsilon by Qnd multiplied by Vbi minus Vgs plus Vx the root. Okay, and in the another case, I already told you when we increase the value of VDS, at that time what will happen? The depletion is increasing, right? And if we keep increasing the VDS, then there will be one voltage where the depletion will be maximum. And after that, if we increase the VDS furthermore, then the depletion region will not increase anymore. Okay, so that point we called is a pinch off point, right? So at pinch off, the depletion region height will be how much? Is equal to A. Okay, so let's put this one in the voltage equation. So what we will get? We'll get VBI minus of VGS plus of VDS. Okay, VDS, we write down VDS sat is the saturation one. Okay, is equal to Q ND multiplied by A square divided by 2 into epsilon. Okay, so that means Vp is equal to Q ND A square by 2 into epsilon. From here, we can write down A is equal to 2 epsilon into Vp0, Vpo divided by Q into Nd, the root. Okay, so this will be the equation 4. Okay, and this will be the equation 3, where we get the Hx and the value of A. Now, let's calculate the current. We here connect the voltage source VDS, and here the current the voltage source VGS. Let's calculate the value of ID. Okay, so here we take this small area, small channel is the dx. Okay, the length of this channel is dx. Okay, and here the depletion region height is hx. Is hx. Okay, so the current flow, the channel for the current flow will be A minus hx. Okay, so the area for the current flow will be A is equal to W multiplied by A minus hx. Okay, and we are considering at that point, in this small point, small area, the voltage drop will be how much? It will be delta of dV. Okay, so let's calculate the current ID. So from here we can write down ID is equal to del V divided by Rx, where Rx is equal to del V rho into dx divided by W into A minus Hx, rho into L by A. Okay, so from here dV divided by dx multiplied by Q value, the value of rho is how much? The value of rho is 1 by Q Nd into mu n. Okay, so we can write down Q Nd into mu n multiplied by W into A minus Hx. Okay, so from this one, Id multiplied by dx is equal to Q Nd mu n W A minus Hx del V. Okay, so if we do the integration, then we will get the value of ID. So the limit of dx will be 0 to L, as the channel length is 0 to this L, right? This one. So the limit will be 0 to L. And what is the value of what is the limit of the voltage? It will be 0 to VDS. So let's do the integration. Now, what we need to do? We need to take the common A. So from here we can write down Q Nd mu n W A 1 minus Hx by A into dV 0 to VDS. Okay, so let's copy this area. If we rewrite this equation, we can write down ID multiplied by integration of dx is x 0 to L is equal to Q N D mu n W into A integration of 0 to VDS 1 minus Hx by A del V, right? Here in this equation, we don't know the value of Hx and A, right? Without these two values, we cannot do the integration. In our last slide, I already calculated the value of Hx is equal to square root of 2 epsilon divided by Q into Nd Vbi minus of Vgs plus of Vx, right? And A is equal to 2 epsilon divided by Q into Nd V pinch off. Now, this is equation 3 and this is equation 4. So now just put the value of equation 3 and 4 in equation 5. So what we will get? Id is equal to Q into Nd mu n Wa divided by L integration 0 to Vds 1 minus Vbi minus Vgs plus Vx divided by square root of V pinch of del V. Okay. Now, please recall that in our last video, when I derived the equation of the MESFET equation in the linear region, at that time I told you the value of this one is how much? This one is the G0. This will be G0, right? So that means this is the channel conductance when there is no depletion region. Okay, so we can write down ID is equal to G0 0 to VDS 1 minus square root VBI minus VGS plus Vx by V pinch of del V. Okay. Now this is a very simple integration. I will do in the next page. Okay. So what we will get? ID is equal to G0. This will be how much? This will be V0 to VDS. Okay. Here V pinch off is constant, right? So we just take out V pinch off. And then we need to do the integration of VBI minus VGS plus VDS to the power half. So what we will get? Plus 1 plus half plus 1 divided by half plus 1, right? I just put this value here. Then we will get VBI minus VGS plus VDS to the power 3 by 2 divided by 3 by 2. This will be Vx, as I need to put the limit first. Okay, limit will be 0 to VDS. If we put the limit here, then we will get ID is equal to G0 VDS minus 2 by 3 1 by root over V pinch of VBI minus VGS plus VDS to the power 3 by 2 minus VBI minus VGS to the power 3 by 2. So this will be the equation 6. This is the current equation. This is the final current equation of MESFET at the saturation region. Okay, so I just write down here current equation of MESFET at saturation region. Okay, so here you can see the current and output current ID or the drain current ID is depend on VDS, value of VDS, value of pinch off, value of VGS and VBI, right? When we just do the practical circuit, at that time VDS we can vary, VGS we can vary, VBI and V pinch off is constant for particular MESFET. Okay, so in my last video I already explained you if we change the VBI, VGS and VDS, then how the current will looks like. That is the IV characteristics. How it looks like? This will be VDS, this will be ID, then it will be like this. For different VGS, this will be VGS1, VGS2, VGS3. Obviously, VGS1 greater than VGS2, greater than VGS3. Okay, so that's all from this video. This is the derivation of the current equation of the MESFET at linear at saturation region. In my next video, I will calculate the conductance of the drain conductance and the transconductance. The formula is the same. Gm is the transconductance. Gm will be transconductance will be delta ID by delta VGS, okay, and the drain conductance GD will be delta ID divided by delta of VDS. Okay, thank you. Bye bye. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.